Ooh, that was heavy. Cool. All right, is everyone ready to get going? No? All right. Well, I'm fairly ready, and we have a fair bit to try to get through. We're going to try to go through as much of exercise metabolism as we possibly can today. There might be, I don't know, like a poppy thing happening at the end of class. I don't know what that means, but whatever. Things that we need to talk about. Hopefully, you recall of like these numbers here, the ATP storage, like about how long that can supply energy. Then after that, the phosphagen or creatine phosphate system, then the lactic acid system or anaerobic glycolysis, more or less, and then following that, the aerobic system. Now, there's a little bit more that I want us to talk about. Do y'all have this slide right here? I hope y'all do. Okay, this is good. So there's quite a few points on this slide that I want you to know and be fairly aware of. So first thing, the rate of ATP production and the capacity of ATP production. Hopefully you see that like 1 meaning the highest, 5 meaning the lowest, just like following charts and things. The essentially like how quickly we can make ATP and how much ATP we can make. Like we could go back and count the amount of ATP from like the aerobic metabolism or anything like that, but just in a general sense, I want you to understand this relationship, that the ATP PCR system, or a phosphagen system, that has our highest rate of ATP production because it's only one enzymatic reaction, the whole creatine kinase reaction, so that's fairly quick. So we can make ATP right there very rapidly. However, the capacity for it, meaning the quantity or amount of ATP, is really low. Now, as we go on a little bit further, if you're following like 0 to 6 seconds, 6 to 30, 30 to 2, 30 seconds to 2 minutes, that would be fast or anaerobic glycolysis. So essentially the end product there being lactic acid. In the muscle, lactate whenever it's transported out. That one is about in the mid-range right there. And then at the very end, we typically get oxidative metabolism 3 minutes or so in. Is everyone good with that? Everyone good with that? So the like oxidative metabolism, everything that's going on, like Krebs cycle, electron transport chain, that has the lowest rate of production because it takes a long time to get through the 10 steps of glycolysis and, I don't know, the many, many steps of the Krebs cycle. I actually forget how many it is, but the capacity is the highest. Like so from like one, like, I don't know, molecule of glucose, how many ATP do we get? 32, yes. So everyone, you probably should know that. It's like that's kind of a big deal. Whereas like from like anaerobic glycolysis, we're only getting like 4 or like 2 net, give or take, right? So we need to understand things like that. Next thing right here that I want you to be somewhat aware of is the work to rest ratio. So this is some things that I think are important, like especially if you're ever like a track coach or if anyone's on track, like kind of the idea behind these different energy systems is we can train them and there's a particular work to rest ratio with all of these. That seems to be the most optimal, give or take. So like for the like phosphagen system, for example, it typically takes around 3 minutes to fully like resynthesize all of our creatine phosphate. But if we're training it, there's typically like a work to rest ratio somewhere between 1 in 12 and 1 in 20. So meaning that if we go for 5 seconds, that we probably need to rest for about 100 seconds. Is everyone good with that? That makes sense? Okay, so like now we're starting to get into like some training recommendations. So if we're trying to get better at that system, like a 1 to 12, 1 to 20 work to rest ratio kind of makes sense. Is everyone good with this? Right? So like 5 seconds really hard, stopwatch, rest for 100 seconds, or like a minute and a half, give or take. Right? So 90 seconds would be a minute and a half. If we're trying to work in the anaerobic glycolysis range, so that one where it's 3 to 3 for rate of production and capacity for production, that one being a 1 to 3 or a 1 to 5, 30 seconds to 2 minutes is typically where that like ends up being. So that's you go really hard for 1 minute, and then you rest for 3 to 5 minutes. This makes sense to people, right? So like if you're a, I don't know, 400-meter dash person, run the 400 in, you know, about a minute or so, like however long it takes you to do it, and then like stopwatch, rest 3 to 5 minutes, and then do it again. And then that would effectively be training that system. Now, down here at the bottom, Like the oxidative system, the last one that I want you to be somewhat aware of, is a 1-to-1 or 1-to-3 work-to-rest ratio. So 1-to-1, meaning that, like, now pay attention here, 3 minutes plus, meaning you have to go about 3 minutes. And then, like rest, 3 to 9 minutes, typically at a lower intensity. So a lot of individuals actually do that with, like, it would be kind of termed interval training. So you might run for 3 minutes, like around your lactate threshold, like slightly above it or slightly below it, like whatever your like protocol like calls for. And then walk or run at a lower pace, well below your lactate threshold, for 3 to 9 minutes, and then repeat. And that's a relatively good way of actually like getting better aerobically or training the aerobic system without doing too much. Now you could just go out and like jog for half an hour, 2 hours, whatever you want to do, but like this actually is scientifically backed in many ways. Cool, we good with this? Awesome. So that's all I really wanted to say there. Now we're going to move into energy requirements at rest and like rest exercise transitions and then recovery from exercise. So a few things to know here. Energy at rest, really big numbers. Probably the biggest one that I want you to know is that 3.5. 3.5 milliliters of oxygen per kilogram of body weight per minute. This, it's not always right, but it's pretty close to being right. The assumption is that per kilogram of your body weight, you're consuming 3.5 milliliters of oxygen per minute. That would be a relative VO2. In an absolute sense, if we did some back calculations, it's typically around 0.25 liters per minute. And I'm not going to make you memorize that one because that's really more dependent on like body weight or body size, more or less. But at rest, it's assumed that we're like getting all of our ATP from the aerobic system, and in that aerobic system, like our blood lactate levels are low, typically around 1 millimole or below, and our oxygen consumption is 3.5. So I would know that. I would know that. Yeah, I think that's all I really wanted y'all to know about that. All right, next thing, rest to exercise transitions. Whenever we begin exercising, we have an immediate increase in need for ATP because it takes a certain amount of ATP to move your body at a certain pace or speed, or to like move a weight at a certain pace or speed. Now, oxygen uptake, there's a lag time here. Like we don't immediately like have an increase in oxygen uptake. It typically takes somewhere between 1 and 4 minutes. So a particular thing about that 1 and 4 minutes, it's on the lower end, the higher in aerobic fitness you are. It's on the higher end, the lower in aerobic fitness you are. So if anybody, like all of the aerobic testing we were doing in lab, how each stage was 3 minutes, there was an increasing workload. So like that 3-minute stage, it's assumed that we're going to get our oxygen uptake to stabilize around 3 minutes. If you're ever designing an exercise protocol for like, or like more of an aerobic test protocol for a really fit person, you can have it be 2-minute stages instead. Or if you're designing it for a really unfit person, 4 and 5-minute stages are frequently used as well. So hopefully that makes sense to all of us, that in the initial like moments or like minutes, we're actually making that ATP to move our body through like space and time, like running on a treadmill or whatever. We're doing that anaerobically, and it typically takes around 1 to 4 minutes, depending on our fitness level, to actually become aerobic in our ATP production. So I'm going to show you something like a graph on the next slide that I think is going to make a little bit more sense. But big terms here. So steady state, already talked about that. Initial ATP production, already talked about that one. So for sure know that the initial ATP production is through the PC system and anaerobic glycolysis. And then the oxygen deficit, the lag in oxygen uptake at the beginning of exercise. I would just know that definitionally. And then I'll move on to the next slide. after I see some pencils slow down. All right, cool.
Could you repeat the
Of course.
steady state thing? So which one was you were more
More fit. Okay, yes, yes.
more time or less time?
Yeah, less time. Less time if you're more.
Quicker if you're
Yes. Yeah. So what Quinn is asking right there is the reason for it being 1 to 4 minutes. Who is it 1 minute for, and who's it 4 minutes for? So we will reach a aerobic steady state, so making all of our energy aerobically, meaning Krebs cycle, electron transport chain, sooner or closer to 1 minute in a more aerobically fit or more aerobically trained individual. And in a less aerobically fit, less aerobically trained individual, it will be closer to 4 minutes. Did I explain that clearly? Yeah. I don't know, it made sense in my head. So, all right. Thank you for asking. Thank you. All right, moving on here. So, oxygen deficit. Let's look at a couple things on here. Like, hopefully you have your stuff pulled out because it is kind of hard to see up here. Like, there's an A, B, and C that I want you to notice is B and C. So there's a particular ATP requirement to run at a certain speed. So if you're running at, in this case, it's 7 miles an hour, there's like 0.7 moles per minute of ATP that are needed. Like, you don't need to know any of that type of stuff, and that might not even be true. But whenever we measure oxygen uptake, like say you go from right here to hopping on a treadmill that's going 7 miles an hour, there's an immediate need for quantity of ATP. Now, if we put on like the medball cart mask that like we actually did in lab, right? There is a lag, and this is the oxygen deficit. So, like if anybody remembers like looking at the like our Parvo Met cart, whenever people would increase given like workload or intensity or just beginning, their oxygen uptake would go up a little bit slowly, right? So that's what's happening here. So the question is, how are we making that ATP? And that's through all of the anaerobic systems. So like, I just want you to get an appreciation for that like the oxygen uptake to do all of this aerobically, it takes a little bit to get up there. Now, some kind of cool stuff going on here. What's happening with like glycolysis or the PCR stuff? So this first thing right here is showing within a muscle what is happening to the phosphocreatine or PCR. So at the beginning of exercise, it drops down rapidly, indicating that we're actually burning that PCR, or we're taking that phosphate and putting it onto ADPs to make ATP to fuel exercise. But after a couple of minutes of beginning exercise, and notice here it starts around 4 minutes and it goes about 7, that's about 3 minutes in total. And that's what I said, it takes typically to get like an aerobic like level intensity. It starts to climb back up after that, indicating that we're no longer using that system, the phosphocreatine system, and we're replenishing it. Is everyone good with this? That makes sense? Now, like rate of ATP production from PCR system, that's effectively saying the same thing. And around 2 minutes, like there's somewhat of a peak in glycolysis, this C picture right here. There's a peak in glycolysis, and then it starts going down a little bit. So that's indicating like anaerobic glycolysis, that it's a little low in the first minute, and in the second minute it goes up more. And then it starts coming down because we're not going to be doing so much like, well, here it's more glycogen, but we're going to do less like anaerobic glycolysis and more oxidative systems. So like burning fat or like using pyruvate to make acetyl-CoA and all of that. Is everyone good with this? That makes sense? Okay, cool stuff going on here. So here's a slide. I don't think you'll have this one, right? No, good. So I don't want you to know this slide. I just want you to understand this concept. That how we can kick at the end of a race. So who's ever ran like a 5K, 10K marathon, whatever? Right? Okay, like hopefully all of you will at some point in your life. How you can kick at the end of it is through something called the creatine shuttle. So whenever you're exercising at a pace below your anaerobic or lactate threshold, then we can start replenishing like creatine phosphate so that we can have high power production later on in the race. So like just kind of a race running strategy. Like typically you want to be like right around your lactate threshold whenever you're like running a race. A little bit before you want to kick, you want to go below your lactate threshold, just like acutely, so that you can replenish a bunch of phosphocreatine. And then at the very end, you can sprint a little bit easier and like pass whoever's near you. So practical application there. Anyone ever going to do something like that? Probably not, just like run really fast like Steve Prefontaine. That's probably what I would do. So, okay. Moving on then, I guess. I thought that was kind of cool. All right. Recovery from exercise. Some more terminology going on here. So after we're done exercising, does your respiration rate or your breathing or your heart rate go back down to your resting levels immediately? No, of course not. So what is that? There's a couple of terms that I want you to understand here. So oxygen uptake remains elevated above rest into recovery for actually quite a while. So there was an old term called oxygen debt. And most scientists use this interchangeably, but the more accurate term is actually EPOC. So this is what I will call it, EPOC. Excess post-exercise oxygen consumption. So essentially meaning that we're consuming an excess amount of oxygen above what we need after the stop of exercise. And the reason for this, and I would know this, like percentage right here, that the amount of oxygen uptake that we're taking in above normal at the end of exercise, only about 20% of it, 20%, I'm going to want you to know that number, is actually used to repay that oxygen debt that we got at the beginning of exercise. And we're going to break down EPOC into two components here momentarily. So hopefully that will make sense. So EPOC, and here it says oxygen debt at the top. Cross that out, it should say EPOC. Because technically, this rapid portion, that's the entire O2 debt, or oxygen debt. The slow portion, that is the continuation of the excess post-exercise oxygen consumption. So after we stop exercising, and I'm going to show you some graphs that are going to make sense here in a second. Right whenever we stop exercise, there's a relatively elevated amount of oxygen consumption. And all we're doing there is we're resynthesizing phosphocreatine, or PC, and replenishing muscle and blood oxygen. So hemoglobin, myoglobin, more or less. So I would know those two things very well for both quiz purposes, test purposes, life purposes. I think that that's important. Now there's a slow portion to EPOC. And that is due to a couple of things. And I'm not 100% sure if y'all have protein synthesis written on yours. But protein synthesis is a relatively important aspect of this. So the first one being elevated heart rate and breathing. So there's an increased energy need due to our diaphragmatic muscles and our left ventricle muscles and things still going. There's an elevated body temperature, so higher metabolic rate. Elevated amount of catecholamines, or epinephrine or norepinephrine, also called in I don't know why I always think about this. Epinephrine in England is called adrenaline. So PKB, AKT, all that type of stuff, right? Or noradrenaline. But yes, so elevated epinephrine, norepinephrine, increased metabolic rate. Gosh, it's Can I tell y'all something funny about epinephrine, really quick? All right, so it's why do you think it's called epinephrine? Does anybody have a guess? Right? So this will come up in our hormone stuff. It comes from the adrenal medulla. So adrenal, ad meaning above, renal meaning kidney. So epinephrine, the functional unit of a kidney is a nephron. So epi, meaning around the nephron, so around a kidney cell. So like that's why physiologists call it that. So, all right. I thought that was cool. That's all right, moving on. Okay, next stuff. Conversion of lactic acid to glucose, or gluconeogenesis. That's going to be through something called the Cori cycle, C-O-R-I. That will come up here in a bit. And then lastly, protein synthesis. So if we have any damaged proteins, we need to make new ones and functionally replace them. So the picture here, I want you to understand this, be able to label these aspects to it. So in this first one, someone is exercising within their aerobic capacity, within their VO2 max. So along with time and oxygen consumption, we begin exercise at a given rate, say 5 miles an hour, 6 miles an hour, 100 miles an hour, it doesn't really matter. There's a lag in oxygen consumption, and that little aspect right there is called the O2 deficit. And after approximately 1 to 4 minutes, or whatever, like however fit they are, will more or less dictate how quickly this happens. They will reach a steady state of like oxygen consumption, and then once they stop, at here it says 6 minutes, there will be a slowdown in, or like a lowering in oxygen consumption. And this really rapid arc coming down, like that really sharp decline, that's called the rapid component. Rapid component, or like what we were talking about before, rapid portion. Rapid portion, component, same difference, right? So you can use either terminology with me there. And that rapid component is repaying that entirety of that oxygen deficit. That's where that's happening. Also, resynthesizing phosphocreatine. And in the slow component, down here, it will be slightly above baseline, and that can persist for a fairly long period of time. That's really more due to how intense the exercise is. Now, something here, this heavy exhausting exercise, a couple of people were talking about the Bruce protocol, and I thought that this was really interesting. So the very ending stage of the Bruce protocol that like nobody makes it to ever, it's going to like 7.5 miles an hour at like a crazy high incline, like 28, 24, something like that. I don't remember what it is, like within my head. But nobody can do that aerobically. It's virtually impossible to actually do. But you can do it anaerobically. So here's a particular thing that I don't want, really high-level physiologists almost forget this. You can exercise at a rate that is over 100% of your VO2 max. Right? So those of you who did like an aerobic max test, like you went at a level, right? That was your VO2 max. Your heart rate was within 10 beats of 220 minus your age. Your RPE was over 17. Your lactate was probably super high. Like we probably weren't increasing the amount of oxygen consumption. But you can go faster. And that's if you revert back to your anaerobic systems. Is everyone good with this? That makes sense? Right? So that's what's happening in this B1 right here. So essentially the reason I brought up that Bruce protocol, many of you can probably run at 7.5 miles an hour on a 30-grade incline for a minute, but you're not going to do it for 3 minutes because, well, like, you're not going to be able to like hang out in your aerobic system that long. Like you won't even be able to match that energy need aerobically. But you can match it anaerobically, like through breakdown phosphocreatine or glycolysis or whatever. So that can certainly happen. And the amount of excess post-oxygen uptake, in particular the slow component, that can stay drastically elevated if we exercise well above what VO2 max is. So if you exercise at like 120, 140% of your VO2 max, then we can get something called the Afterburn. Who's heard of this? Like this is kind of the idea for like how high intensity interval training is really good for like weight loss. And I wanted to go to something really quick. Y'all don't have this slide, but like I'm hopping around. I'll go back to the other ones here in a moment. I think that this is kind of important. And with that, like 226 kcals per day, I want you to know that number. There was this study done in 2013 that they had an individual run one wind gate. Who remembers what a wind gate is? Anybody? Right? What is it, Nick? Yeah. So it's the 30-second max anaerobic power test, right? So like that was the one that we were like computing the different energy system contributions to them. So here, what they found in like approximately an average sized person, just doing one wind gate on a day, elevated their 24-hour like energy expenditure by 226 calories. What application does anybody think that that has? What's up, Bingo? Probably not that. Probably not that. So like people who've had me in other classes, 1 pound of muscle only burns an extra 8 calories a day. So like it's like that one shows up in a different class. I'm not talking about that in here. But like 226 calories. How many calories are you supposed to have a deficit in a day in order to lose a pound of fat a week? What's up, Alec? 500, right? So 3,500 calories is 1 pound of fat. So if you divide that by 7, right, just math, 500 calories a day. What if I told you you can get about half of that in a 30-second sprint on a cycle ergometer? And then the rest of it you can like just not eat Cheetos or whatever. Right? Pretty cool, right? Like, hey, how does P90X work? Just told you, right? Awesome. Moving on. Okay, so on back to here. This, I talked about most of this already, but EPOC is greater following higher intensity exercise, so stuff that's over 100% of your VO2 max, which a 30-second max anaerobic power test, the Wingate test, is well above our VO2 max. Because, well, no one can maintain like their speed for 3 minutes there. But this is like mostly due to like there's a higher body temperature after super high intensity exercise. So we have to homeostatically come back to our baseline temperature. There's greater depletion of phosphocreatine. There's greater blood concentrations of lactic acid, which it takes ATP and oxygen consumption to deal with that. And also higher levels of epinephrine, you know, like epi above or around, whatever, the nephrons, right? So, I don't know. I think that's hilarious. And then nor, what that means, not epinephrine. So it looks like it, but it's not it. So all of that takes oxygen consumption and ATP that we have to deal with aerobically. So hopefully you're good with that. On this next one, this is just a pictorial representation of everything that's going on here. The only thing that's not on here is protein synthesis. You need to include that. Here, I just wanted to show you like where like protein synthesis, like how much ATP that it costs. I don't find that to be abundantly important. Okay, so after exercise, in particular high intensity exercise, whenever you have lactate, where does it go? So lactate, more or less a function of we need ATP faster than we can put pyruvate into the mitochondria. So we export lactic acid out into the blood, lactate, and then we do stuff with it to get rid of it. So I want you to know the classical theory and what the recent evidence indicates. So the classical theory is the majority of lactic acid, lactate in your blood, is converted to glucose in the liver. So that's called the Cori cycle. That's right here. So the idea is, like you do have this picture, it's just way later in your slide set. We'll come back to it. That here, within a muscle, so that's a quad right there, Glucose goes into it. We like exercise really hardcore and all of that. We make lactate. We export it out, and it goes to the liver. And then in the liver, we convert lactate back into glucose. That's called gluconeogenesis. And then we can essentially like export it like back into the blood and send that glucose back to the muscle if we so choose. So that's what we used to say is the main thing that happens. But recent evidence indicates different things. So I want you to get this very well. About 70% of it is actually oxidized for fuel. So where is that? Okay, yeah, right here. Right here, oxidized for fuel. So I'm going to like talk about this picture just a little bit. So initially, that's how it is mostly in muscle. Now, in heart cells, in liver cells, in kidney cells, actually in brain cells as well, we have a different flavor of that lactate dehydrogenase enzyme that leans it toward actually going from lactate to pyruvate. So we make a bunch of lactate in Seroquads from like the 30-second max anaerobic power test. We export it in the blood, and it goes to your heart, your left ventricle. And then, due to the really awesome lactate dehydrogenase like isozyme in there, we can convert that lactate into pyruvate and then put it into the heart muscle mitochondria, go through the whole acetyl-CoA, the whole electron transport chain, and just make ATP that way. Everyone cool with this? Like, is this making sense to everybody? Right? So essentially what I'm telling you is this unidirectionality of pyruvate to lactate. That's typically how it is in skeletal muscle. But once lactate goes out of muscle and goes to different types of cells, mostly heart cells, it will go the other way. Everyone good with that? And then once we have pyruvate, it's super easy to throw it right into the Krebs cycle, especially in heart cells. Okay, everyone good with this? Right? So that right there, that's at 70% of lactic acid is oxidized, meaning it's converted back to pyruvate in different cell types, and we just use it to make ATP. It's more or less all that that is. And only 20% is that gluconeogenesis Cori cycle that we were talking about before. The next thing here, lactic acid within a muscle is moved more rapidly whenever we're doing light intensity exercise. So this is part of the reason. Like, does anybody have coaches that make you do cool downs? Right? Okay, cool. Yeah, so most of us. I'm going to talk about the reasoning for that, right? The idea is that it's going to get lactic acid out and actually converted to energy in the heart or converted to glucose in the liver a little bit faster. So light intensity exercise, about 30-40% of the VO2 max. So I'm not going to ask you to remember 30-40%. Just know light intensity or low intensity. Better start with an L. That seems to help that just a little bit. Now, we're going to go a little bit further right here, since I'm talking about it. Blood lactate removal following strenuous exercise. So like check out this graph. That blue line, that's with no exercise. Everyone sees it going down, right? Now, with light exercise, 35%, they hedged their bets, went right between 30 and 40. It goes down faster. So, my question to you is, what's the application? What can we do with this? Anybody have a guess? What's up, Nick? Yeah. Nick, it's almost like I paid you to say that, because that's actually the application there, right? So the only time that this light exercise after like a more intense bout of exercise is really relevant is whenever you have numerous bouts within a day. If you don't have numerous bouts within a day, it's going to go on its own anyway. So it's more or less just wasting your time. So like if you have if you're a wrestler and you have one match and then in an hour or two you have another match, maybe you can get the lactate out so we have room to make more lactate later. Or if you have like multiple football games in a day, right? Like which can happen, right? But that's more or less the application. That if you have numerous events, it actually is a good idea. Now, if you're done doing a cool down, really isn't worth very much. Now, in a clinical setting, like if you've ever done like cardiac rehab-y type stuff or like whatever, people frequently have them do cool downs. And the primary reason for that is if someone's going to have some like cardiac event, a lot of times it happens after exercise has ended. So like whenever I was working and stuff like that, people would almost always have like premature ventricular contractions like once exercise stopped. And then I would just have them continue to walk on a treadmill more or less until they would stabilize again. It didn't have anything to do with like lactate removal. So it's in clinical settings, that's really wise. Like a lot of negative events happen at that time.
So just like walking around or jogging around would get rid of lactate.
Yes.
So doesn't need to be something like crazy specific.
No. Oh yeah, no, like stretching probably doesn't do anything. Yeah. Now, like certainly, if you want to get the most out of like static or like dynamic stretching, like since your muscles are already warm, they're more pliable. So like that would be a good time to do it. But yeah, outside of that, okay. So next time I'll talk a little bit more about like lactate threshold and stuff. So like obviously we're having a pop quiz. So go ahead and take out a sheet of paper.